All right, hi everyone. Let's get started. So, my name is Asya Magazinik. I'm a professor of social data science here. I'm really excited to welcome you to this talk, to welcome Kosuke Imai to the Hertie School. So I'm going to give Kosuke a slightly lengthier introduction than usual because he's indirectly influenced a lot of you in this room, especially if you take my classes or classes in the Master of Data Science. So Kosuke is a professor in the Department of Government and the Department of Statistics at Harvard. He's visiting us from Oxford, where he's doing a sabbatical this year. Kosuke develops statistical methods and machine learning algorithms for social science research, which means he thinks a lot about causal inference and measurement. If you work in quantitative political science, as I do, it's hard to think of a domain that hasn't been deeply influenced by his work. So from survey methodology and experimental design to algorithmic redistricting to how one measures a neighborhood and works with census data to fairness in AI-assisted decision-making, which he'll talk about today. And if you're a student in the MDS, or if you're one of my students in Stats 2, you've also been influenced by Kosuke because he was my PhD advisor and has worked closely with 3 of the 5 faculty who teach you in the MDS at Princeton, where he worked for 15 years before coming to his current position, where he founded the program in statistics and machine learning. So he's really shaped how I personally teach and advise students, how we've set up the research group here in the data science lab. And Hertie's not unique in this regard. So Kosuke's had an immense influence on our field, not just through his really impressive research, but also through the training of students that he does. His students are at universities literally all over the world, kind of replicating his approaches to research, to teaching and advising. For this, he was the recipient of the Society for Political Methodology's Excellence in Mentoring Award in 2021, and I learned similar awards since then. I'll turn it over to Kosuke. He'll give the talk and we'll have some time for Q&A. The event is officially until 3:30, but we have the room until 4, so stick around after and say hi if you have time. Kosuke.
Thank you. Well, thanks, Asya, for having me. And yeah, thank you guys for coming to the talk. I was competing with this beautiful weather, so I wasn't sure if anyone would be here, but I'm glad to see you all. So I wanted to talk about the project I've been working on last few years, and I'm quite excited about this, and it's still ongoing. The work I'm going to present today is just a small part of it. There's a lot of interesting issues, and so I'm really curious about what you guys think, and looking forward to receiving the feedback. So this is about how the humans interact with algorithms and whether that's a good thing or not. And I'm trying to sort of develop a statistical framework to evaluate this. And I have a lot of collaborators that I like to acknowledge. Many of them are either former postdocs or graduate students. And Jim Greiner is actually a good friend of mine from graduate school. And he's now a professor at Harvard Law School. So when I moved to Harvard, he said, hey, let's do something together. And this is how things started. Okay. All right. So let me first sort of set the stage. And let me tell you what kind of questions I'm interested in and been working on. So as you know, AI and data-driven algorithms more generally are everywhere in our daily lives. We always interact. ChatGPT is my friend. Ask questions and get answers. Okay, but we humans still make many consequential decisions or inconsequential ones. For example, when you do online shopping, you get algorithmic recommendations, but you probably are still the ones who put it in the cart and then pay. Unless you've gone to the point where you say, hey, do a grocery shopping for me, and then just leave it that. I haven't reached there yet, but still, so the humans are making the final decision. Okay. And in particular, we haven't really outsourced these type of important decisions to AI yet. Okay, this is true even though it's not like humans are better decision makers necessarily. We have lots of biases and inefficiencies. Maybe the reason is that we want to hold somebody accountable. Like, I always think humans are causal people. Like, even if you don't take causal inference classes, and we blame somebody, like, you did this, because of your fault, right? That's all sort of causal thinking. But that's not necessarily accurate. Like, humans, thinking is not very accurate, but maybe we want to hold somebody instead of something accountable, okay? So as a result, most prevalent system is something I'm going to call AI-assisted human decision making. Here I'm using AI as a very loose term, as a sort of way to get data-driven algorithmic recommendation. Okay, so humans make decisions with the help of some kind of algorithmic recommendations, and as I said, it involves routine decisions but also consequential decisions. Okay. So here in this space, I'm interested in the following question: how do AI recommendations influence human decisions? Okay. Do they actually help us make more accurate decisions? Does it improve the fairness of our decisions? So these are the kind of questions I'm interested in. Okay. Turns out when I started this several years ago, many people, especially people in the computer science, study the accuracy and fairness of AI recommendations, the algorithms themselves. So there's a lot of articles about the bias of the algorithms and so on. But I felt that that's sort of missing the point. And because the humans are we're social scientists, and we realize that the humans are making decisions. So just because the algorithms are biased doesn't necessarily mean that the decisions are also biased, right? Because the humans is in the loop. So I'm interested in how the algorithmic bias interacts with the human bias and how that leads to certain type of decisions that we observe we make every day. Okay, so today I'm going to show you the statistical evaluation framework for AI recommendations. So this framework is going to be quite general, and it should be applicable to a bunch of different settings. And we are further sort of generalizing the simpler framework that I'm going to present it today. Okay, the idea is to sort of, before deploying these type of algorithms, let's evaluate, make sure that it's actually helping us. And in this presentation, I'm going to talk about experimental study, where I'm going to use the data from that experiment to do evaluation. And in particular, in this experiment, we're going to randomize two treatment conditions. One is the condition where the humans just make a decision with no help. Okay? And then the other one is the human makes a decision with the help of AI. Right? So just to randomize those two conditions. And that's the experiment. Okay. You can do this in observational studies under certain assumptions as well. Okay. And I'll show you the methodology which lets you compare three types of decision-making system: human alone, human plus AI, or AI alone. Like, what would happen if we just get rid of the human and outsource entirely to the AI recommendation? Okay. And I'm also going to show you how to think about how do we optimally combine human decision-making with the algorithmic recommendation. In particular, like, when should we listen to the algorithm and when should we ignore them? Okay. All right. And if I just talk about statistics, it would be as boring as one of those causal inference lectures. So I'm going to talk this in terms of field experiment that we actually conducted and still conducting. Okay. All right, so let me start with the actual experiment, okay, so that like everything is sort of concrete and we can sort of think about what we are talking about. So it turns out that AI recommendation or algorithmic recommendation have been used in the US criminal justice system for quite some time. So I didn't realize this until I studied, and my collaborator / friend Jim is like, you didn't know that? Right, so it's something that I didn't realize. So the algorithm that I'm going to focus on is something called the pretrial public safety assessment, or PSA. Okay, and this is an instrument that's used like when you're arrested, and once you're arrested in the U.S., you'll be brought in front of the judge, and the judge has to make two decisions. first they have to decide whether to release you pending disposition of criminal charges. So you haven't actually been shown guilty yet. So this is just the arrest. Okay? But still, they have to decide before the actual trial happens. They have to decide whether to let you go or not. And if they decide to let you go, they have to think about whether to impose any condition. So cash bail is something that you have to pay money to be released. And they also may add some monitoring condition, like they might put ankle bracelet or something to monitor your movements. Okay. So the goal here for the judge is to avoid the predispositional incarceration. As I said, these people may be innocent, so they don't want to put people in the jail if that's not necessary. At the same time, they want to preserve public safety. So if you're deemed to be pose a risk to the public, they may want you to remain in the jail. Right? So judges, by law, required to consider the 3 risk factors, along with some other factors. But the main ones are the arrestee may fail to appear in court. So if you let a person go, they may not come back for the actual trial. And that would be a trap. That would be a problem. Okay? I'm going to call this FTA. Another risk is the arrestee may engage in a new criminal activity while being on release. Okay? So that obviously it's like a recidivism. Now this is arrest, so you may not be actually guilty, but you still may get arrested. I'm going to call this NCA, new criminal activity. And NVCA is particularly a violent one, and that's something that's of concern. Right? Judge may have additional information we, as researchers, don't observe. So, for example, judge may see the police affidavit, which basically describes the circumstance of arrest. There might be a lawyer in present and may tell you something about the arrestee. Okay? So unfortunately, we don't have that information. So what is PSA? PSA is an algorithmic recommendation to judge. It classifies each arrestee according to these 3 risk factors. So there's a numeric score representing the risk for each factor. It's derived from an application of a machine learning algorithm, unknown. Maybe a logistic regression. It's half joke, not half joke. Okay, to a training data set. It's actually a national database they had, like a relatively large database that they use to train this algorithm. Okay? And it's actually, this particular one I'm going to study is used more than 25 states. Okay? So it's quite one of the most popular algorithms that's being currently used. In 4 states, like New Jersey, it's used statewide. Okay? All right, so what is the experiment? So this is the experiment that we were able to conduct. Okay? And I should give a credit to my friend Jim. He's like incredible. Like if you're in the same room as him, you feel like you should do an experiment. You know the people like that? It's good to have, right? It's good friend to have. Okay, so it's done in Dane County, Wisconsin. Have you been there? It's University of Wisconsin-Madison. Okay, so if you've been there, you've been to that university, that's the Dane County, Wisconsin. In this county, the PSA is a weighted indices of 10 factors. Okay? Importantly, age is the only demographic factor they use. So no gender or race is used. I mean, this is obviously the concern that these factors shouldn't be sort of directly influencing the algorithm. Although, since you've been already taking the ACS course, you probably realize that even if you don't use that for the algorithm, it's correlated with a lot of other things. So, that doesn't mean that the algorithm doesn't discriminate a particular group of people. But at least they don't use that directly. Okay? And then the other factors are drawn from the criminal history record that court has access to. Okay? So what is PSA scores and recommendations? As I said, there are 3 risk factors. Okay? For FTA and NCA, there is a 6-point integer ordinal risk score, 1 to 6, 6 being most risky. Okay. And then for NVCA, the violent new criminal activities, there's binary score. So whether it's seen as risky or not. Okay. And then those 3 scores get aggregated according to, again, the deterministic rule. Okay. And leads to the aggregate recommendation. Okay. So there are 3 categories. One is called signature bond. So what this means is that you can sign a piece of paper and then let go. So it's basically release. Okay. And there's small and large cash bail. So there's small usually means like less than $1,000, and the large means usually more than $1,000. Okay. So there's 3 categorical recommendations. You might ask like, oh, what about like being held unconditionally, right? Like without any condition. It turns out the cases we're analyzing they're petty crimes. They are mostly like stealing something or like drug offense and things like that. There's no murder, for example. Okay, and that's why the harshest decision is like large cash bail, which sort of deters people from getting released. Okay, there's no bonds. Like in the U.S., in some places, like you can borrow money from the bonds industry and then like pay cash bail, but there's no such a thing in Wisconsin. So you actually have to come up with the cash. Okay. So as I said, the judge may have some other information which, unfortunately, we don't have. Which means that, like as a researcher, we have to worry about like things like unobserved compounding factors, like things that we don't observe that still may influence the judge's decision when the judge makes that decision. Okay. So what is the field experiment? In the field experiment, we can calculate these scores for every case. That's easy, it's a little Excel sheet, right, basically. And you can calculate these risk scores and recommendation for every single case. And what's nice about this is that we can then randomize which case where judge gets the recommendation. Okay, so the randomization is the provision of the AI recommendation. Does that make sense? So for some cases, like judge receives the recommendation, in other cases they don't. Some people always ask, wait, why didn't you randomize the algorithm? Okay, that's not ethical. Okay, that's not, you shouldn't do that. Okay, so what we randomized is the provision of PSA. Okay? Even that, you could argue like whether that's an ethical thing. And here, I think the sort of prior most people have is the algorithm is biased, so it must be a bad thing. Therefore, like withholding the algorithm is okay, because this algorithm has been used in this court over the last few years. And so they came to us asking, like, we are worried about algorithmic bias. Can you evaluate this, right? So it's sort of the priors, policymakers thinking, oh, this might be doing the bad thing. So it's withholding that is sort of seen as ethical. That's basically sort of the IRB decision. Okay, so that's basically the experiment. And we have made sort of half of the data publicly available. So you can just go download and play with it or try your other analysis and have fun with it. Okay, so you should check it out. Okay, so here is the actual recommendation that judge gets. So you can see there's 3 scores here. So I told you that the violent criminal activity, new criminal activity, there's a binary score. So in this case, no, so 0. And then there's a 6-point ordinal scores for NCA and FDA. Okay. In this case, you see the charge, which is this person is suspected of delivering heroin. And then these are the risk factors that were used to calculate these. Okay, and I can, if you're interested, I can show you the actual formula and so on. But anyway, these factors are basically putting in a formula. Each different factor is weighted differently, and then produces these scores. Okay, and then at the end, at the bottom, you see the signature bond, which is the overall recommendation, which is also the deterministic function of these 3 factors. Okay, and the rules themselves, the algorithms themselves, is available publicly. In fact, you can go on the website and then see the actual how it, like if you're arrested, like you could actually calculate, okay, what's my score? Okay. So this is important, like from the public policy point of view, because you want it to be transparent, right? Like you don't want some website and say, hey, go enter your information, then like you got 5. Like you have no idea why you got 5. So at least in this case, it's a completely open information, so anyone can see it. Okay. So then what does judge get? Like a judge could even calculate. Oh, yeah, they don't really do that because these are like many cases they have to make a quick decisions. But what's basically like judge always gets this information regardless of whether in the treatment group and control group. So the additional information judge is getting is how these different factors should be weighted. Okay, and then sort of reach to the decision. Does that make sense? So the algorithm is really aggregating the information that judge already have access to, and then showing how to put that information together to reach a particular decision. Okay, so that's basically the experiment. And I want to know how these algorithmic recommendations are actually helping judge, or is it hurting? Okay. All right, so first thing I did is, does the judge agree with the algorithm, right? Because if the judge perfectly agrees with the algorithm, there's nothing for algorithms to do. Okay? So here I'm just looking at the control group where the judge doesn't see the algorithmic recommendation, but I can still calculate the recommendation so I can compare. So human is the judge and the PSA is the algorithm. And you can see on the diagonal, that's where the judge and the algorithm agree. So about 70% of the case that they agree. Yeah, 55, 15. Okay, off diagonal is where that they disagree. So you can see that judge in this case is more lenient than the algorithm. 20% of the case, judge says let that person go, whereas the algorithm says impose a cash bail. And only 9% of the case, the opposite happens. So on average, the judge is more lenient than the algorithm. Okay? Now the next question is, okay, so that's without judge seeing the algorithm. What happens when the judge sees it, right? Then you can just look at the treatment group. So if you look at the treatment group, so this is the judge's decision when judge actually sees the algorithm. One thing you notice right away is that the percentage in the diagonal has increased. So that means is that judge is more in agreement with the algorithm when the judge sees the algorithm. So judge is sort of influenced, right, and nudged towards the algorithmic recommendation. Okay, they still disagree substantial amount of case, about 25%, and we see the same pattern. So the judge tends to be more lenient. Okay. And then the PSA algorithm. Okay, but this is not the end of the story, right? Because this says, okay, there's some inference, actually statistically significant inference, 6 percentage point. But like, is that a good inference or bad inference? Right? That's the really thing we want to answer. Okay, so there's PSA statistically significant inference to judge decision, but how, right? Okay, so that's the question I want to answer. Any questions so far? Is that clear? Okay. Feel free to ask questions, okay? All right, so let me just wrap up the sort of how the experiment works. So there's 2 key design features about this experiment, okay? Obviously, the first thing is randomization. We did it, randomized, human alone versus human plus AI. But the second part is what I call single-blinded treatment, okay? What it means is that AI recommendation affect the outcome only through human decision. So in our experiment, whether the judge provided with the algorithmic recommendation, that affects the arrestee's behavior only through the judge's decision, okay? So this is credible because the arrestees don't know whether the judge actually have access to the algorithm. So there's no way that the provision of the algorithm affects the arrestee's behavior other than through the judge's decision. Okay, so you see that there's no direct arrow from recommendation to the outcome, only through the human decision. Okay? And then there might be some unknown factors, because who knows why judge makes a certain decision, right? I mean, it's hard to know. So there might be some unobserved confounders affecting the decision as well as the RST's outcome. There's one case when the judge actually revealed that judge had access to the algorithm. So one time judge said, well, last time I went against the algorithm and let you go, but now you go rearrested. So I'm going to go along with the algorithm this time. And we're like, don't tell me. Right. But most cases, like judge doesn't let the arrestees know whether the judge has the access to the algorithm. Okay, so that's basically the important feature of the experiment. Okay, so now I'm going to try to formalize this and then come up with a framework that lets us assess the how well the algorithm is, whether algorithm is helping the judge. Right? So I'm going to introduce some notation. So the provision of a recommendation, I'm going to use the ZI. Okay, it's binary. Human decision, judge decision, D. That's also binary. Observed outcome, Y, is also binary. FDA, NCA, or NBCA. I'm going to analyze each outcome separately. Okay? We have, it's causal inference, so we have potential decisions and potential outcomes. So decision is potentially influenced by the provision of algorithms, so function of Z. And then the outcome is a function of Z and D, but we have this single blinded treatment assignment says we can, as long as the decision is the same, it doesn't matter whether it was done after algorithm was given or not. Okay? So this basically says single blinded treatment assignment. And we have randomization, so this second assumption is completely justified, and overlap means that each case has a positive probability of receiving the algorithmic recommendation. So the second and third is just the randomization will guarantee that. First one is the real main assumption that we have to make, but in our experiment, it's credible, and I think in many experiments you could conduct, this could be, you could satisfy this assumption by design. Okay? So what's nice about is the method I'm going to describe after this. There's no more assumption. Okay? These are the only assumption that you need. Yes.
I have a very quick question on single-blinded treatment.
Mm-hmm.
Since the algorithm is public, doesn't the RST have access to it?
Yeah.
And can react based on the estimate?
Right. Yeah, that's right. So the RST could, I doubt they would, check it out, but RST could look at the algorithm itself and calculate their own score, but the RST doesn't know whether the judge has access to it. So Z is the whether the judge has access to it. Okay. At least no RST has asked. Do you have the algorithm? Yeah, but sophisticated RST might ask that question. Okay. All right. So here is the 2x2 table we're going to use to evaluate the decision. Okay. So it's a classification table. So on the rows you have negative decision, positive decision, negative decision. On the columns you have negative decision and positive decision, and then the outcome is negative and the positive. Okay. We're going to focus on y of 0, which is the outcome under release. Okay. So what would happen if you release someone? Okay. So the D star here is the generic decision. So this decision could be human own decision or human plus AI decision, or it could be outsourcing everything to AI decision or any kind of decision-making system. I'm going to call positive decision is cash bail, and negative decision is signature bond. Okay, this is not normative, just the classification-wise. Okay, and the outcome, I'm going to focus on outcome under release. So what would happen if someone gets released? Okay, so y of 0. Because that's the outcome that the PSA is supposed to predict. Okay? So I'm going to call this positive if the NCA happens. Again, it's not normative. Negative if it's NCA doesn't happen. Okay? So once we define this, we can basically come up with this true positive, true negative, false positive, false negative. And I'm going to focus on mistakes. Okay, so false negative and false positive. So what is false positive? False positive is unnecessary cash bail. So y of 0 is 0, that is that someone could be released and that person wouldn't have committed a crime, but judge decided to impose a cash bail. Okay? So that's a false positive. Does that make sense? Like it's unnecessary cash bail. The judge could have just let that person go. Instead, impose cash bail when that was not necessary. False negative is a signature bond followed by NCA. So judge let that person go, but the person committed or being arrested for the new crime. Okay? And that's false negative. Okay? So these are sort of two mistakes that you can think about. So we're going to focus in this case, y of 0 and ignore y of 1. Okay? But actually the framework generalizes to both cases. But today I'm going to keep it simple. Right? So in order to put this in the more formal framework, we have to assign something called loss or negative utility. Okay? So you have to think about, like, because we're going to use statistics, so a quantitative way. So we're going to assign some numbers to what it means to make a false negative and what it means to make a false positive. And if you imagine, like, the false negative and the false positive is a trade-off relationship. Like, on one hand, if you really care about false positive, you don't want to mistakenly impose a cash bail when someone is totally, safe, then you let everybody out, right? If you care about that, a lot more than false negative. But then you might end up making false negative mistakes. On the other hand, if you're too conservative and you always impose, too liberal, and you always let people go, then among those people, some people may get arrested for the new crime. Okay? So we're going to assign this loss, and I'm going to set the loss for the false negative to be 1. And then loss for the false positive to be relative to the false negative. Okay? Because this is not something for me to decide. Like, I'm not going to decide. Right? It's for the judge or the society to decide how much you care about these two mistakes. Okay? So once you assign these numbers, okay, whatever that might be, then we can come up with the average loss, which is basically we call this classification risk. Okay? So the average mistake that one could make. So false negative proportion times 1, because we set it to normalize it to 1, and then false positive proportion times whatever that loss is. Okay? And the law of the statistics is to estimate this under each decision-making system. So what would be the classification risk of judge without AI recommendation? And what would be the classification risk for judge with AI recommendation? And we want the classification risk to be lower if the decision is better. Okay? Okay, that's basically the framework. So we're going to estimate this. Okay? It turns out it's really difficult to estimate this. Okay? Why is that? So first I'm going to look at comparing a human decision with and without AI and trying to see if the risk decreases when we provide AI recommendations. Okay? So the difference in the risk between the human plus AI and human is basically false negative proportion difference and the false positive proportion difference. Okay? Now, there's a reason why this is blue and this is black. Okay? Black is something you can estimate directly from the data. So false negative proportion is something we can estimate directly because these are the cases where the judge actually released with a signature bond decision. So we can see what happens. Y of 0 we observe. Okay? And how many of them get rearrested. We can see that in the data. But false positive proportion is difficult because when the judge imposes cash bail, we don't know what would have happened if that person was let go with a signature bond. Okay, so this is called selective labels problem. And we don't observe y of 0 when the d equal 1. Right? It's a causal inference problem. Okay? And unfortunately, judge is not making random decision, so there is a selection bias going on. Okay? So this thing is identifiable, but FPP is not identifiable. Okay? So each of these terms is not identifiable. Okay? But it turns out the false positive proportion difference is identifiable under the assumption that we have. So what that means is that even though we cannot evaluate each decision makers in isolation, we can actually evaluate the difference between the two. Okay? And it's actually very simple, sort of by randomization. You can flip z equal 1 and z equal 0, and then by law of total probability, you have this. And it turns out the false positive proportion difference is a negative of true negative proportion difference. Okay? Whenever I'm dealing with classification table, my brain hurts, but trust me, this actually works. Okay, all right. So then you can do some fancy double machine learning if you want, but the main message of this is that even though we cannot evaluate each one separately, we can evaluate the difference. So we can answer the question of whether the AI recommendation actually helped the judge, even though we don't know how good they are. Each one. Okay, now I told you that the false positive proportion, false negative proportion, how much you care each one is not up to me. It's up to somebody else, okay? Well, either society or the judge. So you can do something interesting here. Like we can do a hypothesis test. We can say, we can ask the question, when do you prefer human alone versus human AI? Okay? How much do I have to care about false positive proportion relative to false negative proportion in order for me to say, oh, we should have this AI recommendation? Because it depends on that loss. So you can put this in the statistical hypothesis test framework. Okay? And we can invert this test. That is, we can look at the range of the loss where you reject one null hypothesis and then say, under this range, we prefer human alone decision over, say, human plus AI. Okay? So if you reject a null with this loss value, so we just try different values, okay? Then we prefer human AI over human alone. If we reject this null, this hypothesis, then we prefer the other way around. And if we fail to reject both, then we have statistically ambiguous case. Okay? So this way, because the policymakers wanted to know, should we keep using this algorithm? So this is how I can present, okay, you pick a value, right? How much do you care about false positive versus false negative? And then I can tell you whether you should keep this algorithm or not. Okay. All right. Next thing I'm going to do is comparing AI decision with human alone or human AI. So this is a question of what happens if we completely outsource decisions to AI. So get rid of human judge and replace with PSA. Well, maybe better. Who knows? Huh? It's an empirical question. So we want to know what's the risk if we just outsource it to AI. Okay? In this case, you see both are blue, which means both are unidentifiable. Why? Because there's no experimental condition that has PSA at all. I mean, that would be totally unethical. Okay? But it turns out there is some information in the data that you can get to it. Okay? Think about this way. If the human agree with the AI, then we know what would happen if we outsource it to the AI, because we observe exactly what happened when the human agrees with PSA. And we saw that the 70% of the case, they agree. So there's actually a lot of information there that we can extract. Okay? So we basically derive the sharp bounds of the risk difference. So we cannot pinpoint, but we have a bounds, the range of the difference that we observe. And I don't know if you ever use these kind of bounds. Over my 25 years of career, bounds are always uninformative, except this case. Okay? So I was so happy when the bounds are very informative. I'll show you some bounds Okay. So I was like, I'm glad I learned this. First time, it's actually informative. And as I said, the bound width of the bounds depends on the agreement. So in this case, there's a fair amount of agreement. So it actually turns out to be quite informative. Okay. And what's cool about this is that this algorithm doesn't have to be PSA. It could be anything you want. And we can hypothetically evaluate what would happen if we outsource it to large language model. I'll show you what happens if we get rid of the judge and then replace it with a large language model. Okay? And it's very nice because you don't have to run a crazy experiment with the AI alone decision. We can use the existing data to evaluate different kind of algorithm. Okay, and if you want, you can do double machine learning. Okay, and you can also do the hypothesis testing. Under what condition do we prefer AI over human? So you can set the hypothesis test and then see if we reject. Okay. Now, due to the partial identification, we cannot pinpoint. We have bounds. We are basically testing the upper bounds and lower bounds. Okay, so we are basically testing is the bounds below 0 or bounds completely above 0. Okay, so, but you can basically do the same thing. Rejecting the null implies human is preferred over AI. Rejecting the other hypothesis says AI is preferred over human. And if neither gets rejected, it's ambiguous. Okay? And I'll show you the results. Okay, hang in there. One more thing, and I'll get to the empirical results. Okay. So I told you, last thing I want to do is optimally combine AI recommendation with human decision. Okay? So the first thing we asked is, when should we provide AI recommendation? When should we give this AI recommendation to the judge to reduce these mistakes? Okay. So you can think of each case has some characteristics, bunch of characteristics, and then we have a policy which maps these characteristics to binary decision, whether to provide AI recommendation or not. Okay. And you can basically have an optimal policy. So we can minimize the risk. So this is the risk under this policy. So if this is 1, we have human with the algorithm. If this pi of x is 0, we have decision without AI recommendation. Okay? And we want to minimize. We want to come up with this rule such that this classification risk is minimized. So we only want to provide AI recommendation to the human if we know that's going to help human. But we're not going to show it to you if it doesn't help. Okay? You can do this to students. Should we give ChatGPT to student or not? Only when it helps. Okay? Don't give it if it take them to the wrong direction. So it turns out you can do this from the data. You can figure out when is it optimal to provide the AI recommendation. Okay. The second question we do is learning when to follow AI recommendations. So this is trying to help judge, right? The previous one is when should we give it to judge? And then judge gets jealous. Why do you guys decide when do I get the recommendation? So here, I'm trying to help judge. When should you listen to PSA? Okay? So when do we I want to figure out how do we optimally follow the AI recommendation? When we know the AI alone system is better than human decision maker, that's when the human judge should just listen to AI. Okay? Otherwise, judge should ignore. Okay, so its notation is a little crazy, but so basically you can argue, look at the case characteristics and then decide whether or not judge should listen to AI recommendation. Okay, in this case, it's again a partial identification because comparison between AI and judge alone is, remember, it's not pinpointed; it's only the bounds. So what we do is basically we optimize the worst case risk. So only when we know for sure that the AI is better than human, there is a lot of ambiguous case because we cannot pinpoint. It's a bounds. So only when we know for sure the bounds don't overlap with 0, that is, we know that the AI is going to help, that's when we're going to give it to, tell the judge to follow. Okay, so the human decision is like a default. And I think of this as like safe policy learning. Like only when we know for sure that the AI recommendation is better than human decision, then follow. Yeah. Okay, so that's all the methods. That was a lot, but that's all the methods. Now I'm going to show you the results. Okay. Any questions about the bunch of methods that I just talked about? Yeah.
I think there'd be interest in hearing how you use double machine learning.
Oh, yeah? Yeah, so double machine learning is basically like, if we think about like, let's see, like if you think about, any of these estimation, let's go back to the easy case. So like these, these differences, it's technically you can condition X, like all these characteristics, case characteristics that we have. So I could just do like a computer proportion, like differences, the difference in means. But if I wanted to make it more precise estimates, then I would use the case characteristics, which are often predictive of the judge's decision, but also predictive of the outcome. So in the double machine learning, basically you use X, and you can use any machine learning model. And we basically modeling the judge's decision, D given X. So you're just doing some machine learning, any kind of machine learning algorithm. And you're also modeling Y. So the arrestee's behavior given D and X, decision and X, using the machine learning algorithm. And the double machine learning is a way to combine them so that you can get the confidence interval correctly. Okay, so that's how, in this context, that's how it works. So in the experimental study, you could just do the difference means and then, be happy with it. But if you want more precise estimates, like a shorter standards, and in the observational studies, you have to condition X. So in those cases, you have to use, and then double machine learning allows you to be flexible. You don't have to run, say, logistic regression. You can be fancy. You can be a, random forest or whatever, neural network. Okay. Yeah, so that's basically the double machine learning. But you can still get the confidence interval, Okay. All right, so let's look at the results. Okay. So I'm going to show you a bunch of these graphs. So it's important to understand what they are. So on the x-axis, you see the group of people. So overall results, non-whites, whites, female, and male. And I have 3 graphs. One is the misclassification rate. It's a sum of the false negative proportion and false positive proportion, and separately each one. Okay? And on the y-axis, we have how much mistakes are increased or reduced. So if you see anything positive, that means the PSA is actually making things worse. And if you see the negative, means the mistakes are reduced, right? So for this is a failure to appear. And you see that all this confidence interval is pretty much overlapping, except maybe female false positive proportion may have been reduced with the algorithm, right? But this basically shows that the PSA recommendation don't really improve human decision. Even though the PSA recommendation, if you remember, does influence human decision. Like the judge is being influenced, but sometimes it's in the right way and sometimes it's in the wrong way. So it's sort of canceling out, Same thing for new criminal activities, and same thing for NVCA, right? And the confidence interval is pretty tight here. This is 20 percentage point, right? So it's like, it's being influenced, but it's like a wash in terms of accuracy. Okay. Now, what about comparing PSA alone with judge? What would happen if we replace judge with the PSA? Okay? Ultimate algorithmic. Apparently, in some courts, some of the courts in China, they have AI judge, and AI judge decides everything. So, that could happen. And so here is the failure to appear. Again, the PSA, positive means PSA is making more mistakes than the judge alone. Okay? Negative means PSA is actually making less mistake. It's a comparison. And remember, it was a bounds. So the thicker line is the bounds, point estimates, and then the 95% confidence interval outside of it. Okay? So what do you see? Like if you look at the false positive, it's actually PSA is significantly worse than the human. Basically false positive, remember, it's an unnecessary cash bail, right? And among the non-white in particular, you see that PSA is being unnecessarily harsh compared to a human judge, okay? And male. You can see that, and as a result, overall, because even in Wisconsin, Dane County is like 90% white population. This sample is like half non-white. Yeah, so it's non-white is overrepresented. But this is happening without reducing the false negative proportion. So the algorithm is being unnecessarily harsh compared to the human, but they're not reducing the false negative proportion either. Okay? And you see this same thing for new criminal activity, right? Again, like non-whites. Here it's like, right, there's nothing going on here, right? And new criminal activity, look at that. Like it's all across the board, the PSA is way too harsh. They think that someone is going to commit the violent crime if they're released, even if in reality they don't. Okay? So in this case, the judge is being more lenient than the algorithm, but in the right, that seems to be correct. Okay. So I told you that we can do a hypothesis test, and we can say, well, maybe algorithm is being harsh, but depending on which mistakes you care more about, maybe you prefer algorithm. Okay. So here I'm showing you the ratio of loss, how much you care about false positive versus false negative. So higher than 1:1 means like you're going to care false positive twice more than the false negative. And this is like 100 times more than the false negative. Okay? And the green means human alone preferred, and dotted means ambiguous. There was a pink, which means AI alone preferred, but because we never prefer AI alone, I didn't put the pink here. So you see that basically, like if we care about false positive mistakes way more than false negatives, we basically care about human alone, right? Decision. This makes sense because false positive is unnecessary cash bail, and if we care about that, right? If we don't want to make that mistakes, then the human would be the better one to make a decision. Okay, and especially if you're non-white or male, that's what you would prefer. And same thing for NCA, and same thing for NVCA. For NVCA, even if you prefer false negative a little bit, you still prefer the human judge over PSA. Okay. All right. So last thing is how to optimally combine PSA with human decision. So here I'm going to show you that when we should provide the PSA provision to make the decision better, more accurate. And the darker blue is the cases, these are number of cases, where we should provide the PSA recommendation to the judges. And the reason why you have so few cases here, because the whole data set is actually about 2,000 observations, is because this is the only cases where the NVCA flag is 1, and these scores are quite high. Okay? So what this means is that we should only provide this PSA recommendation if the PSA recommendation is saying this person is really, really risky. In other cases, providing the PSA recommendation is actually not helpful. Okay? And the same thing when to follow the PSA recommendation. We only find the extreme cases. NVCA flag is 1, and the FDA and NCA score is pretty high. Only these cases, you should be following the PSA recommendation. Okay? So this shows that the PSA is useful only in cases with extreme recommendations. Okay. Lastly, so a lot of people complain about PSA. That's a horrible algorithm. Not very sophisticated. So we can Well, okay, maybe try something else, okay? So we're going to use the maybe real AI, that is large language model, okay? So this is the prompt I gave to the large language model. We use the Llama 3, which is the open source Meta large language models. It's open source, so it's actually, you can replicate the results, okay? So I told the Llama 3, you are a judge in the Dane County, Madison. You're asked to decide whether or not arrestees should be released on their own recognizance, which is basically a signature bond, or be required to post a cash bail. If you think the risk of unnecessary incarceration is too high, then the arrestee should receive own recognizance release. On the other hand, you should assign cash bail if the following risks are high, and I gave 3 risks that they should be considering. And then we give basically different characteristics of our arrestees. And so this particular arrestee has the following characteristics, and then we give all the PSA inputs. Should this arrestee be released on their own recognizance or given cash bail? Please provide your answer in binary form, 0, 1, and followed by a detailed explanation of your decision. And, these large language models just provide some reasonable looking paragraphs, and Jim says, that's B+ in my class at the Harvard Law School. So that's pretty good, right? And then now we can say, okay, what would happen if we just use this and completely replace with a human judge? Like, is it better or not? And so that's why this method is useful, because you can actually evaluate the algorithm that you didn't use in the experiment. Okay? And what you see is actually Llama 3 in this case, it's quite harsh. So it's like increasing 25 percentage point the false positive proportion compared to the human. Okay? Maybe there's some reduction of false negative, but it's quite it's more lenient towards the women, but otherwise there's a lot more false positive proportion. And same thing for the NCA, same thing for NVCA, and it's even worse. Okay. So just a side note, after this, I told the Llama 3, you're being too harsh, okay? And then I asked the same question again, and then the Llama 3 decided to release everybody. Very obedient, easily manipulated judge. Okay, so just let me wrap it up. So we propose a methodological framework for evaluating these different decision-making systems. I think it's quite widely applicable. You can imagine medicine, doctors getting recommendations before making a treatment decision. Technology companies, online advertisement, obviously. So single blinded treatment assignment is pretty easy to implement, I think, in many cases. Applicable to RCT and observational studies. Don't require AI alone decision. That's important. And there's no assumption other than unconfoundedness and the overlap beyond the single blinded treatment assignment. Okay. We have a software package if you have an experiment like this, and check it out. It's called AI Human. And we did this RCT, and then we find that basically PSA recommendations don't improve over human decisions, and only extreme PSA recommendations are useful. Both PSA and AI decisions perform worse than human decisions in the sense that they're basically being too harsh. Okay? We have a bunch of extensions of this framework into multiple decisions, joint potential outcome, considering, what would happen if you actually give a cash bail, and then also dynamic decisions, people get arrested multiple times, and so how do humans interact with the algorithm when you repeatedly interact with that type of recommendation system? So I'll stop here. Yeah, thank you.